Yeah, perfect. Thank you. Sorry. First of all, good morning, everyone. Today we are going to discuss about artificial intelligence in additive manufacturing. Sometimes you're familiar with artificial intelligence and additive manufacturing. And firstly, I want to tell that additive manufacturing has moved far beyond its origin as prototyping tool. In the older days, this subject is called as, sorry, they're having a cheese rock. It's called rapid prototyping and tooling. Nowadays, it's redesigned or recalled as additive manufacturing. Today, it's an integral component of advanced manufacturing strategies across aerospace, automotive, energy, medical industries. And at the same time, artificial intelligence has transformed a theoretical construct into practical, enabled real-time decision making, defect process, and process optimization. By using in vast areas. Nowadays, we know that artificial intelligence is used in almost all sectors. Next slide, please. Overview of additive manufacturing. In this session, I will explain about what is additive manufacturing is. I will give a brief explanation about, brief history of additive manufacturing. Also, I will explain about artificial intelligence, how we can incorporate these two technology for a better printing. Yeah, first of all, let's start by clarifying what we mean by additive manufacturing. In simple terms, additive manufacturing is a method of fabricating three-dimensional structures by successive addition of materials, guided by a digital design. Sorry. This stands in sharp contrast to traditional manufacturing in all means, which often relies on subtractive process. You know that the conventional manufacturing right now we call the subtractive manufacturing process, and this another one that is additive manufacturing. Why we call this subtractive manufacturing? Because it's we are removing materials from a large block. In additive manufacturing, the idea is elegant, beginning with nothing and through a controlled deposition process, construction only what is required. So there is no waste at all. This layer by layer approach not only reduces waste, but also allows geometries, which is currently impossible by normal manufacturing. You can see that the heat exchanges what produced or printed by using additive manufacturing is nearly impossible by conventional manufacturing process. The significance of its method lies in its versatility. It has enabled a rapid transformation from digital design to physical artifact, compressing decision cycle dramatically. Next slide, please. Mm, This is a funny slide because we are discussing about the brief history of additive manufacturing. The additive manufacturing, the term originally originated in 80s or late 80s. You can see two images over here. The left one is a printing. This is the first print ever did. It's the first technology in additive manufacturing ever did by Dr. Hideo Kadama. He's a Japanese professor. And this is a replication of his first printing. He destroyed his first printing of disappointment. He initiated this technology in 1980. He got the patent. It's called photopolymerization. Nowadays, we call this VAT polymerization also as well. And he invented this method and this technology. He patented this. He contacted many industries. He applied for several funding. He was a professor at that time. And as normal, he doesn't get any funding and he doesn't get any support from the industries or anywhere. So he fed up with the academic terms and he resigned his job and worked as an engineer the rest of his life. At the same time, the next one is the example of laser sintering process. It's introduced by Joseph Householder. He is a engineer in US. The idea behind that one is really funny. One day, after completing his job, he is driving through desert in Las Vegas. While he driving through Vegas, he saw that sunlight is focusing or sunlight is falling on sand dunes. Then he thought that why we need to focus a particular light in a particular area to melt materials and to create layer by layer structure. And it's also happened in 1980s. And he prepared that one is the exact one he prepared by using sand, right? This early efforts laid the foundation, but adoption was initially very slow. You saw that it's 1980s it started, but it's booming right now. At that time, the hardwares were prohibitively expensive and the available material was predominantly limited. In 1980, stereolithography as the fused deposition modeling became available commercially. You can see it's 1980s. They prepared that one. It's commercially available as 1990s after 10 years. Still, it's not vastly available. Next slide, please. Importance and significance. Now let us understand why additive manufacturing matters. You can tell us different steps I explain over here. Firstly, design flexibility. AM enables topology optimization, where material is distributed according to stress path, often resulting in organic, lattice-like structure. Nature itself become a design partner. As engineers replicate the efficiency of a bone or a core-like geometry. That's nearly impossible by conventional manufacturing process. Second, rapid prototyping. Um, in older days, if we have a concept, you need to design in everything. Then we need to different manufacturing sector, machining, welding, different kind of things, and we need to make a prototype. But right now, it's very quickly we can manufacture things. Third, customization and personalization. Those are key things of additive manufacturing. In medicine, for instance, patient-specific implants are created that conform precisely to anatomical requirement. It consumes goods for food waste to eye waste, personalized in rapid become exponential rather than a luxury right now. And material efficiency is for a conventional manufacturing, it typically weighs or 30 to 40% of the materials. But in additive manufacturing, we can attain a material up to 90% or higher than 90%. So the material efficiency is very high. Designed for functionality, that is lightweight and material optimization. For example, additive manufacturing allows to embed cooling channels within turbine blades. That's nearly impossible by subtractive manufacturing. Integrated multiple parts into monolithic structures or produce components with greater material properties. These are one of the design flexibility and design functionality as well. And you can see one person over there. He's a scientist in NASA. He's working in an international space station. And you can see there's a image of a wrench over there. One day he required a wrench to operate one machine in some repairs or tightening in International Space Station. He reported NASA, and what they did is the NASA sent an SPL file to International Space Station. By using that software, they printed that. But they already the International Space Station already have a 3D printer over there, so he can print the wrench. Older days, if somebody tell about these kind of things, it becomes science fiction. Now these are realities, and or image is sending over there, and it will be converted into a product. And also in US Navy ships, they're using the same thing. They have metal printers in almost all the Navy ships. In the sea itself, they can prepare different kind of prototypes. Next slide, please. Application of additive manufacturing. Due to the limitation of time, I'm going a little bit fast. Sorry for that. And you can see that different materials we can see. Is first one is an engine housing for a F1 racing car. You can see the topology of that housing is highly complicated. This entire thing is manufactured by using additive manufacturing. And second one is an electric motor. We all know that there are different components in an electric motor, different type of materials. And this entire electric motor is printed by using additive manufacturing. And Still, we can say that additive manufacturing is comparatively expensive compared to conventional manufacturing. But the beauty is the medical, you can see the medical implants, we can produce customized medical implants for different patients, but wherever they require. Because we all know that all human beings have different physical requirements. So in the older days, in India, we know that we have the Jaipur legs, right? In the older days, all the people who lost their limbs using a uniform size limb. So it's create a huge pain for them. Right now, we have customized bionic limbs, which exactly perform just like our normal limbs, and it's 100% customizable. It's all because of the support of additive manufacturing. Next slide, please. And this is the difference between conventional manufacturing versus additive manufacturing. You can see that there's two images over here. First one is a top-down process, just like old statues, old monuments. We can see that all how those statues were built. We take a huge block of stone or metal piece, we carve the metal or the stone, and we remove the unwanted parts, and we get the exact size or shape we require. But most of the materials produced by in this method or the wastage are going to be 100% waste. We are not supposed to recycle. And you may think that in metals we can recycle, right? But the problem behind the metal is we are using different kind of coolant, different kind of medium over there. So nearly impossible to recycle because we need to wash, we need to prepare those for recycling, and for those recycling process itself, hi- highly expensive compared to producing in new material from ore. So people are not considering or recycling those material. And in second stage, you can see an intriguing and complicated design by using additive manufacturing. And this entire structure is by using a fused deposition modeling printer. And there is no waste at all. You can use entire material by itself. There is no, sorry, 0% waste. That's the beauty of this bottom-up process. Why it's called bottom-up process? We are printing the bottom layer first, then go to the top layer. Next slide, please. Why additive manufacturing booming now? Firstly, the availability of design software. We have modern CAD and simulation package allows engineers to create highly complex geometries and validate them digitally before manufacturing. That's really good. Though for conventional manufacturing is not possible. Parameters modeling, topology optimization, and generative design have removed previous bottlenecks. Wide selection of second one is wide selection of printable material. In the older days, if a scientist want to make something, or if not only the scientist, anybody want to use the 3D printer, they want to prepare the materials. Right now, we know that almost all kind of printable materials are available. We have materials from metal, ceramics, polymers, and even from super alloys, high-end rep alloys are still available. So a wide selection of printable materials are available right now. And push to net zero and sustainable manufacturing. Government and industry facing stringent carbon reduction target. In UK itself, there is a motto: by 2050, all the industry should be net zero. So if here we have a huge opportunity for additive manufacturing. Additive manufacturing, with its superior material efficiency and capacity for lightweight, direct construction to sustainability goals. Next is improve automation combined with better precision. For example, the feedback control lasers, high resolution sensors, and closed loop monitoring has enhanced reliability and repeatability, enables industrial scales production. And finally, government and industrial investment. Uh, in Europe, US, almost all the different sectors, they are using additive manufacturing widely because of this fabrication process. Still, I'm going to tell that there are limitations for additive manufacturing, but compared to the limitations, we have higher flexibility, higher production rate, better product quality can be achieved by additive manufacturing. And so the government and industries are pumping money for this kind of industries. So right now, additive manufacturing is thriving. Next slide, please. And there are n number of additive manufacturing process. And today I'm going to discuss only about selective laser sintering because of the limitation of time. Among the many additive manufacturing techniques, let us focus on selective laser sintering. You can see the image over here. One of the most widely used powder bed fusion method. We're using powder for this one. The principle is straightforward yet powerful. A thin layer of powder is spread across a building platform. You can see over this roller is spreading. And there is a laser beam guided by digital design, selectively fuse the particles where solid material is required. The platform then lowers fractionally. Another layer of powder is applied and processed repeatedly until object is complete. It's a continuous process. The beauty of SLS, sorry, I have a sore throat. The beauty of SLS lies in versatility. It's highly versatile. It can produce a broad range of materials, include polymers, metals, ceramics, because the surrounding powder support the pass during fabrication. In most cases, we don't require any kind of support in for this kind of thing, so we can eliminate those parts and wastages. But depend upon the design and density in some cases, and rarely we require some supports. But in most of the other 3D printing, we require supports. Right? Next slide, please. So, constraint and challenges in additive manufacturing. Uh, Still, there is a lot amount of materials available for 3D printing, but still, as a researcher, we need to tell that there is not much materials which are required to print or the materials what we require to prepare a high performance material is still not available. And the process control, the thermal gradient of additive manufacturing are extreme. Local temperature can exceed several thousand degrees Celsius. Cooling rates can reach millions of degrees per second, and such conditions create complex microstructures. We will discuss about it later. Maintaining the consistency across an entire building remains a formidable challenge. It's really for those who are working in additive manufacturing know these challenges. Material properties. Air part often display anisotropy, with mechanical strength difference between building directions. This is one of the constraints everyone facing. And right now we are using artificial intelligence to limit these challenges. We will explain those on later slides. Build quality and defect. There are different kind of faults happening while we are using, especially for metal additive manufacturing. Wrapping, porosity, lack of fusion, residual stress are common. Next slide, please. You can see over here in this image, there's a columnar grain in the left side, and there's an equiaxial grain. And, and if you have columnar grain, the tensile strength of that print is comparatively poor. And by using controllable printing, we are able to access equiaxial grain. And if you are able to access equiaxial grain in a printing, the strength is comparatively very high. And the second is the hardness. And that's one of the key factor, distance of top of deposition. And what's the distance between the top of each layer of deposition is highly influence the hardness. And second one is the defect, lack of fusion. You can see that surface roughness, agglomeration due to these things are happening, the surface roughness, and how to avoid this defect by using in additive manufacturing by using what we can say artificial intelligence. I will explain those things in later slides. Next, please. Introduction to machine learning. To appreciate how machine learning assists additive manufacturing, let us first clarify what we mean by the term. Machine learning is nothing but a subset of artificial intelligence that enables systems to improve their performance through data-driven learning rather than explicit programming. In the context of additive manufacturing, machine learning models ingest data from sensors, simulations, and hostel building of identified platforms. In my previous presentation, I explain about these kind of things. And it will also help to predict outcomes and recommend adjustments and optimization as well. And we can see the overview of machine learning, types of machine learning. The first one is supervised learning, which models are trained on labeled data. We can give a labeled data for them. We can feed, for example, different kind of images of birds, and then we shows the image of another animal to ask them whether this is a bird or not. And the machine learning can spot that it's not a bird, because how their understanding is a bird having different particular features, it having a beak, it having wings, it having feathers, this kind of stuff is called supervised learning. And second one is the unsupervised learning, where model uncover hidden structures without labeled data. For instance, clustering sensor data streaming to detect anomalies. This is one of the superior things we are using, unsupervised data. And reinforcement learning, where algorithms learn by trial and error. For example, we are showing some images of the birds, and it's showing another bird. So the algorithm understanding a bird has different features. They give equal weight. Initially, they give equal weightage to beak, their feather. The birds are able to fly. These kind of features they give equal weightage. Then we show the image of a penguin. It tells that it's not a bird because it doesn't satisfy all the criteria initially. Then the reinforcement learning tells that no, it's a bird itself. Then it reduces the weightages it's give to fly and wings. So the algorithm understand that not all the birds able to fly and not all the birds having feathers and these kind of structures. So the weightage will be reduced automatically. It's a continuous process. It's called reinforcement learning. And it's not supported by any human nowadays. It's done by the algorithm itself. The beauty of machine learning lies in its adaptability. It's not limited to one problem type, but can be applied across the center of additive manufacturing workflow, from design to post-processing. Next slide, please. ML in process optimization framework. These things I explained in our previous presentation, but if the people doesn't able to attend the previous presentation, I'm just giving a brief idea about this thing. Data pipeline. First of all, we are collecting data from different things. For example, here we are considering this additive manufacturing system, and we can collect from thermal cameras, acoustic sensor, machine logs, image of building surface, all provide valuable input. And we are collecting all this data. Some are gray data, some are explicit data. Next is future engineering. Raw data must be converted into meaningful descriptions such as average melting pool temperature, scan path deviation, and powder distribution, anomaly or uniformity. These are in future engineering. And third stage is model training and validation. We get the data, we features this data, then we need to model training and validation. This is the key steps over here. And the supervised models such as neural networks, mostly we are using neural networks or support vector mechanism, are trained on historical data to predict defect likelihood or mechanical properties. Validating ensures that these models generalize to unseen blinds. Almost these are in this stage we can identify what are the errors in this trending and how to rectify these errors and what are the things we need to do. And finally, the key stage is real-time optimization. One moment, please. Here, sorry. Here AI closes the loop by dynamically adjusting machine parameters during this build. For instance, if porosity is predicted based on thermal signature, the system can reduce scan speed or increase laser power to correct the mid-process. This capability transforms additive manufacturing from a trial and error operation into predictive adaptive manufacturing method. Next slide, please. Process optimization in additive manufacturing. You can see there are n number of variables over here. To predict scale of complexity, consider the variable in a typical laser border fusion is given over there. If we attempt to test all these combinations, all these parameters, could you please click the next because on this slide there is, oh yeah, you can see that. D- No, please, yeah, thank you. You you can see these very important parameters for additive manufacturing of this one. You can see there are different kind of process parameters. If one way, one way to attempt to test all possible combinations empirically, even with just 12 key variables, each at two levels. Considerably, we are doing 5 levels, and here we consider a person is doing the experiments just two level, the high and low, and we are having 12 parameters. That means we need to do 4096 experiments. Imagine a PhD scholar is using the conventional RSM or any other kind of Takuji method for this 12 parameters, two levels, and it's giving an experiment for 4096. And if a PhD scholar is able to do one experiment per day, he requests, and every 365 days, without any leave or anything, continuously, he required 11 years to complete this all experiments. If he able to success one experiment per day, it took 11 years, more than 11 years. So it's horrible when that person going to graduate. So in this case, we are using artificial intelligence to reduce this optimization. We consider what are the factors influencing what are the things. For example, previously I mentioned, if there is a defect, it's a fusion defect, we find out that we are not considering all the process parameters, we consider the key factors. For example, the temperature. How temperature influencing these fusion defects. These kind of things we are studying, and we are correlating these things. So we not really going to optimize all the process parameters. Next slide, please. And these are the different type of problems in additive manufacturing. First one is called regression problem, and second one is called classification problem. And the example for regression problem is control of geometry, grain size, residual stress, distortion. And the machine learning problems we need to use is linear regression, neural networks, Bayesian networks. And for the classification problem, for example, there are control of defect information, solidification morphology. And for these kind of problems, we need to use decision tree, random forest, support vector mechanics. These are the key two types of problems in additive manufacturing. Next slide, please. You can see that a control grain, the grain structure over there, the grain goes in computers using Monte Carlo method. This one is happening over by using, in this study, they did Monte Carlo method. And then microstructure features such as grain size and orientation determine mechanical properties. You all know that in additive manufacturing, rapid solidification lead to heterogeneous grain structures. With simulation grain growth in 2D, you can see that one. Often which columnar grains align along with building direction. That is one of the key problem. In our previous slide, I saw the columnar grains back there, and we need to reduce those size. Is mostly in along the print direction. Using machine learning, we can correlate process parameters with grain evaluations. We can study, and you can see these two images compared to the previous one. Process parameters with grain evaluation. Sorry, previous one, please. Previous one. Thank you. By using additive manufacturing, we can control the process parameters, not the explicit process parameters, the factors which influence this grain structures. We can control those process parameters, and we can make a refined grain structure print. Second one, please. Next one. And this is the lack of fusion. This defect arises when insufficient energy density prevents complete bonding between layers. This or many times while you are printing, these kind of defects will happen. This results in porosity, poor mechanical strength, and often catastrophic failures. If you're supposed to take this for tensile strength, we can see that the ultimate tensile strength, and the void size. Depend upon the void size, how the strength is influencing over there. And by using tailored printing, um, we can remove this one by using artificial intelligence. If you are using machine learning, we can, for each layers, if you are using a sensor and data, we can find out that what is the temperature they generate over there, what are the type of green structures, these kind of things we can study, and these data will be fed to our machine learning algorithm, and the algorithm can change the process parameters and variables, and we get a uniform size of print. Next slide, please. And see, this is the fusion defects we mentioned before. You can see in this image, this red area is called the fusion area. And in normal welding, we call the weld pool. Nowadays, it's called the fusion area for 3D printing. And in the bottom image, you can see this uh, fusion area. There's a void over there because of this hatch spacing. Hatch spacing is nothing but the distance between each layer we are printing. And in normal cases, while we are printing, we are not able to identify these things because while we are printing, we see that it evenly printing in each layer. But after solidification, while we are going for testing, we can find out these voids in between. And what are the ways we to avoid these things? We need to close this one because we need to reduce the hatch spacing, right? Normally everyone can get that idea, but there are a number of problems. When we are closing the hatch spacing, the temperature may rise, and another kind of fusion defect, if the temperature increases, there's a cause for residual stress will increases, and that will cause defects to this particular material. So by artificial intelligence or machine learning protocols, we can't control these temperatures for each layers while we are printing. And through this way, we can reduce the hatch spacing and reduce the size of the print, and we can eliminate this kind of fusion defects. The fusion defects are mostly due to two types of things: less amount of temperature and higher amount of temperature. To these two factors are influencing. While we are reducing the hatch spacing, we need to be control the temperature very well. If you are not able to control the temperatures, again fusion will be happen over there. Next slide, please. This is how we are able to reduce lack of fusion. You can see over there. First of all, we need to collect the data. In older days, what we are doing is we conduct so many trial runs or the trial experiments, conduct different kind of process parameters, different values. Then we need to find out what is the lower values, what is the better result. Then we take those values as a levels, the lowest level and higher level. And then we go for optimization process. Then machine will predict the optimized parameters. Then we conduct the experiments. Again, we need to compare these values. And it's a time-consuming process. And if you want to get a final result, it's not possible, right? So right now, we don't want to conduct all the trial runs. Instead of that, we need to collect the data from the literature itself. If it is open access, we can collect all the literature. We can feed those uh, article itself to the machine learning algorithms. Whatever we are creating, there are different methods of creating machine learning algorithms. We are those data. There are not one or two data. There's n number of data available. We feed those data. We pipeline this data. Then it will predict. For example, we print a materials for matching steel. We need to print for stainless steel, and the only data is available for matching steel. And we feeding those data, and we are giving what are the properties of this another stainless steel. This machine learning algorithm will change those things compared to what are the requirements. We tell that the data we only having matching steel, and the things what we need to print on stainless steel. So, and we telling that what are the difference between these two materials to machine learning, and they will understand this content, and they will rewrite the optimized process parameters for us. And through this machine learning content, we can find out which one is the better process parameter combination to reduce the lack of fusion defect. Clear. Next slide, please. You can see over here, after the optimization, the hatch space is reduced, and at the same time, the temperature is controlled. You can see that heat input per unit length and pole width, how it's influencing. And there's two images, two data showing that over here, which one having a still having defects, and these are for different materials given over there. Next slide, please. Machine learning for defect detection. There are three principal approaches. One moment, I'm not able to see the slide. Oh, what happening? Yeah, machine learning for defect detection. First, image-based detection. It's very simple. Using computer vision, cameras mounted inside AM chambers captures image of each layer, convolute neural networks then analyze these images, identify anomalies such as incomplete fusion or powder irregulation. That based on image-based detection. Everyone using in the older days as well. Sensor, sensor-based detection. Acoustic sensors detect vibration characteristics of spatter or cracking. Thermal sensors monitor heat distribution across the build. Vibration and optical sensors provide additional layer of monitoring. And these are sensor-based detection. Machine machine language for anomaly detection. Unlike rules-based system, machine learning can detect subtle, non-obvious patterns, indicate of defects, which is not normally is identified by human eyes. This improves both speed and scalability for printing. The advantages are clear. Compared to a human inspection, this detection is very fast, high accuracy, and potential for closed-loop correction. In industry, this transition into low scrap test. We need to reduce the test in industries, reduce instruction cost, and higher confidence in part reliability. These are the influence or advantages of ML. Next slide, please. Data sources for machine learning in additive manufacturing. Types of data I have already explained in our previous presentation again. Process data, machine setting, environmental conditions, sensor data, in situ monitoring. Always key remember is in situ monitoring. In many of the sectors or many of the academics doesn't having this facility in situ monitoring in different things. But if anybody is going to apply for a funding or something, the key thing is in situ monitoring. We can real time access the data. It's really key. So all the researchers over here was watching this presentation, they need to give more importance to in situ monitoring data. That will dramatically change your print quality. Next slide, please. Challenges and limitations. While potential of AI in additive manufacturing is remarkable, several challenges remains. The first one is data scarcity. Unlike field like image recognition, where millions of labeled data exist, but still, AM databases are small and fragmented. Generated large data sets requires costly experiments. The second is computational cost. Training deep learning models on high dimension sensors data is resource intense and it's really struggling. So for we are not able to incorporate each and every parameters over there. So there's a training or we need advanced softwares for this modeling. Mm. Or mostly we look at GPUs or specialized hardware. The third one is model interpretability. Many ML models act as black boxes. Engineers and regulators hesitate to accept prediction that cannot be explained. It's not only for the engineers, all the researchers are doing the same. Explainable AI is therefore a critical research frontier. Finally, ethical concerns. An overall reliance on AI risks. Sometimes AI is not able to identify all the data. Is it is a manipulated data or real data? Because still machine learning or these algorithms are in the baby steps. We need to advance those things. And in those steps, what we are doing is we are incorporating a human intelligence, or especially human with AI. So initial segregation, whenever the AI having a doubt or something is happening in the algorithm, it can rectify by using a human being involved in those things. Next slide, please. Future trends in machine learning for additive manufacturing. Integration of deep learning and real-time feedback system. Emerge a convolutional natural network analysis, belt pool images, milliseconds and correct laser port instantaneously. That's going to be happen in this next era. We can rectify all the errors in a fraction of seconds. In a fraction of seconds, the machine can adjust its parameters. Digital twins. The same times we can create the replica by using a simulation package, and without doing any destructive testing, we can do all the simulation package on this digital things, and we can predict what are the things when they require any maintenance or any corrections will happen. Third, autonomous AM system. Here, machines not only detect and correct defects, but also optimize their own parameters across built learning continuously. And this is happening right now. The machine learning is self-correcting things. We are approached the era of self-correction, self-optimizing AM cells. And I believe that quantum computing may accelerate the optimization, enable rapid exploration of vast parameter space that are currently implaceable. Next slide, please. And conclusion, we begin with the foundation of additive manufacturing, its history, significance, and application. When then examines challenges, limited material process variability, and persistent defect. And then we talk about artificial intelligence, offer solution there, process optimization, defect detection, and prediction modeling. And we also explain about the AM transformation, sorry, AI used in AM for reactive process into proactive one, cost decrease defect and minimalization, and perform enhancement, how to remove those old defects related to fusion and different parameters levels. And finally, we can reduce cost by using predictive modeling as well. I hope you're having a basic understanding of these things. Next slide, please. Next slide, please. Thank you. I welcome your questions and reflections. I know that I'm a little bit fast because of this started very late.
Thank you very much, sir.
You're welcome.
So as we can see, there are no questions from the participants.
Okay. If they have any queries regarding anything, they can write me an email.
Sure,
Anytime.
sir. We will share all the panelists' email address with the participants. So if they
Yeah.
if they have any queries, they will ask.
Yeah, sure, no problem at all. Most
Okay,
welcome.
sir. Thank you, sir. So we can
Good day.
conclude this session.
Yeah.
So thank you very much, sir, for
You're most
delivering
welcome.
such an insightful and engaging lecture on additive manufacturing process. Your session provided us with valuable perspectives on the application of artificial intelligence and machine learning in additive manufacturing processes as their role in shaping the future of Industry 4.0. I'm sure the participants have gained a deeper understanding of the subject and will be inspired to explore it further. Sir, on behalf of the organizing committee and all the participants, I extend our heartfelt gratitude to you for for taking the time to share your expertise with us today. Thank you very much,
Thank you
sir.
very much. You're most welcome. Good day,
Thank
everyone.
you, sir. Thank you, sir.